All right, here we go. See how many you got. How about number 1? What's the next term? Mason? 1. Oh, here. Kidding. Just kidding. There we go. All right, how about number 2? What's the next one? Yeah. 99. What was the pattern here on this one? What did you notice? Like, how did you get to 99, Jared?
It was
Like,
write down patterns.
So like this went up by 6.
That went up by 6. That one went up by 10. That one went up by 14. So it's plus an additional 4 to the boxes.
Yeah, exactly. All right, how about number 3? What was the next one, Lilia? Negative 1 over 32. And did you notice the pattern on this one? Yeah, or you could say multiply by negative 1/2. Yeah, there you go. All right, how about number 4? Alex, did you get that one?
I have 23.
You are correct. All right, 23. So with this one, it wasn't that you were adding the same thing, but it was increasing by 1 every time. All right, how about number 5 was probably the most difficult out of the 6. Does anybody feel really confident about what they got for number 5? Yeah.
Did 217.
Ooh, it is. How'd you get it?
The difference is, well, you have to, first the differences go 1, 7, 19, 37, etc.
Yeah.
So the differences increase by 6 each time and go 6, 12, 18, 24. And it goes on and on like that.
Oh, interesting. I didn't look at it like that. Okay, so you said it went up 1, up 7, and what was this one?
That one was 19.
19. Okay, so then, that had a difference of 6,
Yeah, and then
18.
it goes 6, 12, 18, and it adds 6 each time on those differences.
Ooh, okay, that's really cool. That's really cool. I didn't think of it like that. That is really neat. Did anybody get 217 and thought of it? I thought of it in a different way.
How did you think of it?
Well, I'll tell you how I thought of it. If you think of this was 0 cubed plus 1 gave me 1. This is 1 cubed plus 1. This was 2 cubed plus 1, 8 plus 1. 3 cubed, 27 plus 1. So I thought of it as the number cubed. Well, it was but 1 less, I guess. Maybe n minus 1, the quantity cubed. Oh, but I like that, Eddie. That was really cool. All right, how about number 6? Anybody feel confident? Yeah, Lilia?
65 and 64.
Yeah, there you go. 65 over 64. So down in the bottom, do you notice you are multiplying by 2, right? You can also think of it as 2 to the first, 2 to the second, 2 to the third. Up in the top, I found my differences were 2, 4, 8, 16. Do you notice that's 2 to the first, 2 to the second, 2 to the third, 2 to the fourth? So that's kind of cool. Again, 7, 8, 9, I'm going to leave as a challenge. If you want at the end of class or even tomorrow, ask me, I'll tell you what I got. All right, so let's get into some definitions. I'm going to give you about 20 seconds, and I want you to read that paragraph definition, and then we'll talk about it. All right, what are some words that pop out at you? Just shout them out. What words jump out? Pattern. Okay, that's really good, okay? A sequence is going to have a pattern. What else?
Natural numbers.
Ooh, natural numbers. This is going to be important. Domain. Oh, what's domain? We struggled with this last year. What's domain? Possible x values. So we're saying the domain, and what's another word for domain? Besides possible x values, they're the, yeah, they are horizontal on the graph. You're going the left and the right, but not necessarily x-intercepts. They're the input, right? Okay, so domain input. How about the sequence is an ordered list, okay? It's an ordered list that follow a particular pattern. I want you to look at this first example with me. 5, 8, 11, 14, 17, 20. So we just saw in the definition that the domain is the set of natural numbers. So this is the first term, the second term, the third term, the fourth, the fifth, and the sixth. So the term numbers are the x values. The term numbers are the x values. The outputs, or the y values, are the term values. So, and we're going to use, I'm going to start with function notation. You remember f of x and g of x from last year. I'm just going to use, instead of x, I'm going to use n for the term numbers. So, because they're natural numbers, that's why we're using an n. So if I have 1, 2, 3, 4, 5, and so on, and these are the outputs, I plotted these points. What does this graph look like? It looks linear. It looks like a line. And do you remember from Algebra 1 and Algebra 2, how do you know if the graph is the graph of a function? Vertical line test. It's the vertical line test. So if I can draw a vertical line anywhere through the graph and it crosses at most once, it's a function. So this is a function. Now, let me ask you something. Can I connect the dots? No, I mean, for this situation, could I connect them? No, because what does it, sorry. No, we can't. Because what does it mean when you connect between 1 and 2? When you draw the line and say, it's everything in between there, right? That's what connecting it means. Is there a 1.1 term? No. Like, it's the first term, the second term, the third term. So, if I want to come up with an equation for a line, what formula do you remember that helps us write an equation of a line? Music to my ears. Y equals mx plus b. All right. Well, when you look at a line, slope is rise over run. How high does it go up between the values? 3. So guess what? The common difference, if it's linear, okay, this is only true for linear. The common difference is the slope. So I now know if they go up by 3, my slope is 3. Even though I don't have b, can I figure out what it is if I follow the pattern backwards?
Yeah.
What would the b value be? 2. So guess what we're going to do? So y equals mx plus b would be 3x plus 2. But we're going to use this notation. F of n, so instead of an x, I'm going to write 3n plus 2. So when you're ready, flip the page. And I will give you guided notes the majority of the time. Once in a while, I'll ask you to take your own notes. All right, in addition to using our typical function notation, sequences have their own special notation using subscripts. For example, we can refer to an entire sequence as x sub n and a sub n. So instead of it being f of x, in sequence notation, we might call it x sub n. But that represents the entire sequence, the entire list of numbers that are in a special pattern. And we can use other letters like A sub n, G sub n. An individual element, we write like this. X sub 1 would represent the first term. You know what, if you put a heavy book on it, or your backpack, you put it on the corner, that usually stops it. Maybe we need a static backpack. Anybody else go back?
Yeah, right here.
Let's try another one. There we go. Alright, so x sub 2 is the second term, x sub 3 is the third term, and so on. So this is just perhaps new notation for you. So if we go back to our last example, where x sub n, I'm going to call it 5, 8, 11, 14, 17. What is x sub 1? 5. What's x sub 3? 11. It's the third term. All right, x sub 10. It doesn't go out to 10 terms. How can you find it?
Look at the sequence.
Okay, what do you mean look at the sequence?
Well, it goes by 3 every time.
So are you saying you just keep adding 3?
I mean, you could do that.
You could do that. That works. What else did we do on the last slide?
You can plug it into the equation.
You can plug it into our y equals mx plus b formula, right? So we called it f of n was 3n plus 2, so wouldn't that be 32? But there's nothing wrong with adding 3 to get to the next one, until what you need. All right, so sequences have two types of formulas in general. One of them is called the explicit formula. And the explicit formula gives the nth term. What I mean by that is just like on the last slide. If I wanted the 10th term, I can plug in 3 times 10 plus 2. If I wanted the 99th term, I would do 3 times 99 plus 2. So the explicit formula is super helpful. We have something called a recursive formula. There's a very, very famous recursive formula called the Fibonacci sequence. You may have heard of that, and we'll tackle that this year. The recursive formula gives you the nth term based on the previous term. But a recursive formula has at least 2 parts. It usually gives you the first term, and then how do you get the next term? So let me show you what this means. Alright, so in our same example, the explicit formula for x of n, we already did that one. It was 3n plus 2. So that's explicit. If I want a recursive, it has 2 parts. I have to tell somebody what's the first term. So we write x of 1 equals 5. Then I need to tell people, how do you get the next term from the previous? So if I want to represent the one that's in front of n, what does the term in front of n look like? Like with a letter.
N minus 1.
Awesome. This would be n minus 1 is the one in front. And then what did we do every time?
Add 3.
We added 3. So now, if you were in Algebra 2 last year, you may have learned this notation. We're going to need to say that n is greater than or equal to 2. That's not the new stuff. But here's the other part. We need to say that n is an element, and I'm going to use capital N. That stands for natural numbers, because they're not 1.1 or, fractions or decimals. So let me go over this again, because I know this is new. So this says little n, which is our subscript. This looks like a little e. It's like a sideways e, is an element of, and the capital N stands for the natural numbers. How many of you saw the little e thing last year? My students did. Okay. All right, so then it's new for the rest of you. So just, again, it's just the Greek letter, epsilon, and it means is an element of. So we have to clarify that n is not any number. Because, you could have decimals, negatives, square roots, all sorts of stuff. All right, so that's the recursive. So here's the next example. What I want you to do is I want you to do as much of this slide as you can. And it's okay if you can only do one part. We'll eventually get there. All right, if a sub n is the sequence 12, 7, 2, negative 3, and so on, find the next term and describe the pattern in words. If you can handle doing the explicit formula, now let me ask you this. Looking at the list, how would you know if this is linear?
Yeah.
What do you mean nothing
Yeah.
repeats?
You can't have the same, feel like that. Same point.
Ooh, I like the word there. Yeah.
The differences between the terms are the same each time.
Okay, so and I think that's what you were saying. Like it has to be when you plot them,
Yeah.
they have a common difference, and it would be like describing a line. So let's look here. So what's happening between the terms every time?
Mine's 5.
Good. Okay, they're going down by 5. So you subtract 5. So if it has a common difference, it's linear. Let me say that again because it's really important. If there's a common difference, not going like when our intro part, you remember we had one that went up by 3, then 4, then 5, then 6. That's not linear because they weren't going up by the same amount. It didn't have a constant rate of change. But if it's linear, you can use y equals mx plus b to find the explicit formula. If it's not linear, we're going to learn how we do it another way. And that's for tomorrow. Okay? All right. And then I think some of us can get to the recursives. We might be able to do that. And then I think a sub 20, a sub 21, a sub 22. So do as much of this slide as you can. And again, it's okay if you can only do one at this point. And I love what I see looking back. Okay, how did we set up that recursive? And maybe you can do part of the recursive, not all of it, but maybe part of it, and that's okay too. All right, what was the next term in number 1? What was the next term?
Negative 18.
Negative 18, and we said subtract 5, so it is linear. So my slope is the common difference, and then to get the b value, you have to go backwards one term, okay? Because this is the first term, the second term, the third term, the fourth term, the fifth term, the sixth term. So the y-intercept would be, if we had one, the 0th term. So what would b be? 17. So now watch how we're going to do this. You don't want to use x, because that's not the letter we have. It's going to be negative 5n plus 17. Okay? All right, the recursive formula. You need to state the first term, and you just pay attention. The letters will change, okay? This sequence is described by a sub n. So the first term is 12. And recursive just tells you what you have to do to the previous one to get the next term. So the previous one is a sub n minus 1, and then we said subtract 5. Now, I put this on here, maybe I didn't explain it very well. Why do I say n is greater than or equal to 2? Why don't I say n is greater than or equal to 1? Why, though? Why? What happens if I put 1 in here? That's 0, and I don't have stated a sub 0, like I'd be stuck. And then I'm going to say that n is an element of the set of natural numbers. Again, a recursive formula, the difference between explicit and recursive formulas. Explicit will give you any term you want in the list, like the 8th term, the 50th term. A recursive formula formula only gives you the next one. Okay? So watch how I end up using a combination of both in number 4. If it says find a sub 20, I'm going to go plug it into the explicit formula. And I got negative 83. But then I flipped to the recursive and said, okay, if I want 21, I just subtract 5, and I get negative 88. Subtract 5, and I get negative 93. So do you see how I use both explicit and recursive to do this? Do you see if I did explicit on these two, that's a lot more work than I needed. All right, questions so far? All right, let's try the next one. G sub n is 3, 6, 12, 24, 48, 96. Is this linear? No, so you cannot do y equals mx plus b on it. That's why I tried to say it on the last slide. All right, so go ahead, try 1, 2, 3, 4, as many of those as you can. Have the right idea. It's 3 times something. Just think about this and like test it. Test it. You're close. You're really,
I
really
haven't
close.
done this in a while.
Yeah, I know. It's an algebra 1. Okay, so what do you do to get to the next one? Multiply by 2. So make this one times 2, and that'll give you the next term. All right, number 1. What was the next term? 192, and describe in words what's happening.
Multiply by 2.
Okay, multiply by 2. All right, a recursive formula. Here we go. G sub 1 recursive has 2 parts. The first term, and then what are you doing to get the next one? We're multiplying by 2. I personally prefer to put, if I'm multiplying, the multiplier in front. It's not wrong to say G sub n minus 1 times 2. It's equivalent. And then I need to say that n has to be greater than or equal to 2, and n is a natural number. Sorry, that looks kind of funny. That's a capital N. All right, number 3. Find G sub 7 and G sub 8, in case you can't read that. Number 3 says find G sub 7 and G sub 8. Don't we have G sub 7 in the list?
Yeah.
Yeah, actually, or no.
It's
Oh, we just
190,
found it,
yeah.
right? We just found it. So then G sub 8, I'm just going to multiply by 2, 384. All right, now this one's tricky, but I think somebody in here can figure it out. Explicit. Anybody Did you come up with it, Eddie?
Yeah, I got
What'd you get?
G of n equals 2 to the n minus 1 times 3.
All right, nice work. You were so close. You just had them flipped.
I just had to switch it around.
Yeah, you were really, really close. Okay, and we're gonna figure out tomorrow how you come up with this one. But you do start with 3, and then like I don't want to say 3 times 2 to the n because that would have given me 6 to start. So I had to go back 1. So that's why it's the 2 to the n minus 1. All right. On the last page, let's look at this one, and then you notice I X'd out, I accidentally copied one of the sequences again, so we don't need that last one. All right, this one, x sub n is 1, 4, 9, 16, 25, 36. The first question I have for you, is it linear? Am I adding a constant every time? No, so there's no y equals mx plus b here. So let me give you a moment, and there's several ways to look at this. Okay, there are several ways to look at this one. But do as much as you can, 1 through 4. If you can only do 1, that's okay. Last year if I sat on it, it would stop. I can't sit on it the whole period. It's really hot by the front of it. All right, did anybody figure out what's the next term?
49.
49. All right, anybody? There's a few different patterns. What's one pattern? You said you added 3 and then add 2 more like this, like that? Okay, yeah. Lilia?
Square 1 and 2 and then 3 and
Oh, okay, so look at this. If you look at the term numbers, that this is like the first term, the second term, the third term, couldn't you just square them? Oh, so guess what? My explicit formula, because I'll tell you, if you look at it with the 3, 5, 7, 9, that certainly will give you the next term, but that's really difficult to write an explicit formula for. So then x sub 25 would be 25 squared. Isn't that 625? All right, and now I'm not going to reveal the recursive formula today. So those of you that want to work on it, you can, and I can tell you tomorrow what it is. All right, so let me real quick. Okay. 1. Start. Video. Okay.